All right, good morning, everyone. Happy Friday. So let me just tell you, we're going to wrap up Unit 1 today. So we're going to wrap up the unit on system modeling and block diagram reduction. So let's pick up a little bit before where we left off last time. I'm going to send you to the PowerPoint screen. Okay, so we left off with the DC motor model where we had, I think we had the single unified transfer function, which looked like the motor torque constant divided by this polynomial, which is the impedance of the armature times the characteristic polynomial of the motor itself, and then plus this other term out here. So in the S domain, this is the transfer function from the armature voltage to the speed of the motor shaft. I want to highlight a couple things that I didn't get to on last lecture. And in particular, I want to point out that the poles of this transfer function are not the same as the poles in the other blocks of the system. So remember, we got this by using our feedback reduction rule on the block diagram that looked like this. Sj plus Kf, and then in feedback, a gain of K sub B. All right, so we used our block diagram feedback reduction rule to change this image in the top right to this image in the left. And I just want to point out that the poles up here in this diagram, well, I mean, these are two separate transfer functions, so they'll have two different sets of poles. But the poles of this guy are negative RA over L and negative KF over J. And I just want to point out that if we look at this polynomial down here, the poles are not going to be there. I mean, they would if either Km or Kb were 0. But in particular, this is one of the fundamental hurdles or things to comprehend in this class, is that when we close the loop around systems, the poles of the new system, or what I will eventually call the closed loop poles, are different than the open loop poles, or the poles in the open loop system. And that's going to be both a blessing and a curse for us as controls engineers. It's going to allow us to take systems that are otherwise poorly behaved, put them in a control loop or in a feedback loop, and change how they behave. Now that cuts both ways. We can also take a good behaving system and end up making it perform poorly if we do our jobs wrong. So just a heads up there. Okay, so this we said was a second order system. Its poles are going to be, I don't know where. I'd have to solve this polynomial knowing what all the constants were. If we make the assumption that the inductance in the armature is small, then I said we can reduce this to a first order system. So then we get the transfer function from voltage to speed as being what, Km over, well, just drop the L out of the expression above, and we get Ra times Sj plus Kf plus Km Kb. Okay. So things to note about this system are now it's first order. And that means, well, that means and is meant by only one pole. And I guess the last thing to do would be to kind of determine where that pole is. So remember that a pole of a transfer function is an S value that makes the denominator 0. So our job now is to rearrange this denominator to find the S value that makes it 0. So I think if I can not run out of room down here, I can factor the denominator and make it look something like this. So what did I do? I pulled out an RA from the bottom and I stuck it, I guess I stuck it up top. And then I did the same thing with the capital J. And yeah, then I isolated the S and I got these terms all alone by themselves over here. So the pole is going to be at the negative of this value. So whatever that is, negative times all that stuff. And right now this isn't terribly meaningful except for the fact that all of these constants, all of these K constants were positive, right? So the Kf was the friction constant. That means the faster we go, the more friction there is, so it's going to be a positive number. Km was a motor torque constant. The more current, the more torque, so that's positive. Kb was the back EMF coefficient. The more speed, the more back EMF, so that's positive. J is a moment of inertia, so think of that as like a mass, and it's going to be positive. And Ra is a resistance, so that's going to be positive as well. So my point here is that if I take a bunch of positive things and I tack a negative sign on it, that tells me that the pole is going to be in the left half plane. So here's our first pole zero diagram of the quarter. This is, again, the real axis and the imaginary axis. And the important result of this analysis is that the pole of this system is in the left half plane, which means it's going to be a stable system. That means if I input a bounded voltage, I'm guaranteed a bounded speed. It can't run away from me. Any questions so far? All right.
Yeah, actually, I had one.
Yeah, go ahead.
Oh, never mind. I just noticed that if L is approximately equal to zero. Why are we making that approximation again?
If we don't, it becomes really hard to determine where the poles are. It's a pretty common approximation, although it's not terribly realistic because the whole idea behind a motor is that you're using the magnetic field to drive the shaft. But to mathematically analyze it, it makes our lives a bit easier to drop that second pole out.
Gotcha.
Yeah, good question. Okay, so we didn't actually start this example with any requirements, but one of those requirements might be pick a motor that achieves a certain time constant. I think that's pretty much one of the only ones we can do. So I'll copy from the old slide. Km, J, Ra, and then this stuff. I'm just going to call it P for pole. And so we established that this pole is sitting out here at negative P. And I don't know, we could, well, here's an idea. We've just analyzed the transfer function from voltage to speed. Now what happens if we did all this work and you come to your end of quarter design meeting with your boss and he or she says, oh, we needed the motor to go to a certain position, not a certain speed. And you say, oh, you should have told me that. But actually, you're not hosed because you know that position, theta, if you differentiate it, that gives you your speed in the time domain. And all we have to do is take the Laplace transform of this relationship, and then we get S times big theta equals big omega of S, assuming zero initial conditions. Which means the transfer function from omega to theta is just 1 over S. And so we can use that information to take our old transfer function, which was voltage to speed, and convert it into a transfer function of voltage to position. So Km over JRA divide by S plus P times S. Okay, so in red we had the pole zero diagram of the voltage to speed system. And if we consider the transfer function from voltage to position, we earn ourselves a pole at the origin. So this guy pops up there. So this means that if we want a bounded position as the output of our system, if I input a bounded voltage, I'm not guaranteed a bounded position because we have now integrating pole here. Okay, so to summarize, if say we were to input a voltage versus time that looked like a step, that's nice in a bounded signal, then the speed, omega of t versus t, is going to behave like a first order system. It's going to exponentially rise till some bounded steady state value. But if you look at the integral of this signal, this omega signal, that's going to look like a ramp eventually. So this is the theta of t versus t signal. So this signal is bounded. This signal is unbounded. And that's the consequence of this pole at the origin. Okay. So all that means is that if you need this motor to spin to a fixed position, you need to be either very careful about what inputs you give to it. So clearly a step input won't work. Or what we're going to do in lab is we're going to close the loop around this motor. So what we're going to end up doing is nesting feedback loops. Right? There's no reason why you can't have one loop in here and then another loop out here. All you'd have to do is you'd have to reduce this inner loop first, and then you would reduce the outer loop, and then the process repeats itself. Okay? All right, so the next slide in the packet is a summary of a bunch of block diagram reduction techniques. Let's see if I can make this smaller. Okay. So a couple of these we've seen already. In particular, we have seen the transformation number 1, which takes 2 blocks in cascade and allows you to multiply their transfer functions. So this is a way to reduce the number of blocks in a system. And it is kind of cute that you can represent either G1 times G2 or G2 times G1 in linear time invariant systems. It doesn't matter which one comes first. You get the same product result at the end. You might also want to move a summing point downstream. Or you could think of that the other way as the G block being copied here and then back there. That would allow you a nice clean signal here as X3. Another common operation is if you would really like this pickoff point to happen upstream of the G block, then in order to have X2 be the same signal in this diagram, we need it to be X1 times G. And so the way that you would accomplish that is you would copy another copy of G into the feedback path. All right, that's slightly better. Except all the annotations are still there. All right, I'll figure this out eventually, by the end of the quarter. All of those operations have converses, so you can undo them as soon as you do them. Here the idea is, nope. Here the idea is I can move a pickoff point downstream, and if I do that here, this signal X1, if you just do the algebra around the loop, this is 1 over G times this signal, which is X2, but X2 is just X1 times G. And so again, this is just a reminder that these Laplace block diagrams are a pictorial way of representing algebra, basically, or even arithmetic here. Okay. And then here we can again move the summing junction either upstream or downstream of a block, provided that we accommodate that block in the feedback path here. And then rule number 6, this is the big E that we derived last lecture. I'm going to make repeated references to forward over 1 plus forward times feedback. That's how I'm going to be saying this rule number 6. Any questions here?
I do have a question on number 5.
Mm-hmm.
I'm trying to understand the equivalence of what the x2 times that block, that feedback block, the 1 over g. Is that multiplying that 1 over g by x2 and it's being added subtracted by the incoming signal x1?
Mm-hmm. And then that sum is then being multiplied by g. So when you would use this is if you needed to move the G block to the quote-unquote other side of the summing junction. And you can do that provided you also invert it and put it down there. So let's write out the algebra, what's going on in the left-hand diagram. This diagram says that x3 is x1 times g plus or minus x2. I think that's how I would translate that picture into an equation. And over here, we have that x3 is g times x1 plus or minus x2 over g. And so if you distribute this g out, then I think you get equivalence between these two x3s. Does that make sense, Jeremiah?
Yeah, it just looked kind of weird. And I was following the math if I was to multiply these things together in a cascade form. And I guess I just didn't realize that the extra g on the right side when you're deriving it is distributed.
Yeah, this guy's pretty crucial.
Okay.
Cool. All right, what comes next is a exercise. So usually when I do this in a face-to-face lecture, I would put this up on the monitor and I would challenge the class to reduce this block diagram into a single block. I don't know how well that's going to work here online because part of that exercise is me walking around the class and answering people's questions as they come up. So this is going to be one of the unfortunate differences between face-to-face and online. I'm just going to do this exercise and not give you a chance to try it out first. So I don't know of a better way to do it than that. What I can show you is just my immediate thought process of how to reduce this transfer function. So first off, I see that there are nested feedback loops. There is a loop here, which I'm going to call loop 2. And there is a loop here, which I'm going to call loop 1. And if I were to simplify loop 1 and loop 2 into single blocks, then I think I could express the rest of the diagram as follows. 1/2 into a summing junction that goes into loop 1 and then into loop 2. And then the output of that is y of s. And then there's a feedback between y of s and this summing point here. So that gets its own little mini transfer function. So the main point is I'm giving you a preview of how the solution is going to go. If I can collapse loop 1 and loop 2 into their own single blocks, then I can iterate this block diagram reduction process. So let's get myself some new screen real estate and show you how that would go.
Clay?
Yeah, go ahead.
It seemed that you were going to try to condense it down to the drawing that you drew up above. You chose the right side to collapse. Is that just out of preference, or are you trying to break it up into parts and then combine them both together? Say, do the right side first, then the left side, and then combine them both.
Oh, sorry. The right side, the what I denoted as L2, I think it was just more obviously a feedback loop.
Oh,
I
okay.
think what I might want to also point out is that this is the first time we've seen a triple summing point, and I just want to point out that that is the same as two summing points in Cascade. And so yeah, how I usually draw this is I break up this mega circle into two littler circles, and then
Hmm.
this cut line passes through that point. Sorry, yeah, thanks for reminding me. That's one of the outcomes of this diagram is that you can take a summing junction and split it into many summing junctions.
Would you prefer to have two connect, say, in this case, like you said, there's three uh, parts to it, or parts going to that summing node. In that sense, would it be, like you said, easier to break it off into like 1, 2, and then 1, 2 for the other one?
So I don't know if I understand what you're asking
Oh,
because uh,
because
a summing junction isn't really meaningful if there are less than two inputs. So here there's only two inputs, so there's nothing really to break up. Here there's three inputs, so I can break that into two summing junctions, each with two inputs.
oh, that's what I meant. Sorry. Yeah,
Okay.
there's three going, but you said like you do 1, 2, and then 1, 2, like 1/2, and the oh, never mind. I think I see what I did.
Okay.
So when you broke it up into like each loop, you just like labeled it like a variable name, like I guess L1 and L2.
Hmm.
So is it better to always kind of, I guess, like do that and then just like break up your like I mean like simplify your system and then at the end go through each loop and then break that down like individually?
Um,
So like
so certainly, like breaking a large, complicated problem into smaller subproblems, that's like a general tip for problem solving. So yes, um, this particular system is quite complicated. So I don't know if there would be actually a good way to do it otherwise.
okay.
Cool. So we have L1 as being 20 over s plus 1 over 1 plus 20 over s plus 1 times s over s plus 2. So this numerator is the forward path of loop 1, and this denominator is 1 plus the forward path of loop 1 times the feedback path of loop 1. So again, this is the name of the game in this class. We got nested fractions all over the place. So let's go ahead and clear those fractions by multiplying the top and the bottom by s times s plus 1 times s plus 2. So we end up with 20 s plus 2 over s plus 1, s plus 2, plus 20s. Okay, so we see that loop 1 is a subsystem that is third order with 1, 0. And go ahead and stop me if you have any questions on this algebra. Otherwise, I'm prone to just kind of firing through it.
Is it like a parallel circuit? How you get that original circuit, original expression?
This equality right here, the L1 equals.
The part next to it.
But the I think
Yeah, I'm
this is
using
proving.
feedback rule number 6 from the prior slide. So it's not product over sum, if that's what you're thinking.
Okay.
This is, if you like, this is G over 1 plus GH, right? That's the simplification rule I'm using. So let's see that again in loop 2. The forward path is just a gain of 1/4. The feedback path is s plus 2 and s plus 1. My pluses are not really showing up here. Okay, so I can multiply everything by 4s plus 1, and I get s plus 1 on top, and then 4 s plus 1 plus s plus 2. All right, so now I can rewrite my block diagram. I've got a factor of a half, and then a summing junction, and then an L1 here, and an L2 here, and then 1 over s plus 1 in the outer feedback path. So if you like, we can call this loop 3, which is going to be L1, L2 over 1 plus L1, L2 times 1 over s plus 1. Now, L1, L2 is a really complicated expression because it takes this polynomial and multiplies it by that polynomial, or that fraction by that fraction. But if you were going to try and answer the original question on the slide, which was what is the overall order of this system, I actually think we're poised to do that right now. So L1 has a third order denominator. L2 has a first order denominator. So if I multiply these two fractions together, L1, L2 will have a fourth order denominator. And then if I multiply L1, L2 by s plus 1, or I guess divide by s plus 1, this will have then a fifth order denominator. And if I multiply top and bottom by that denominator, then L3 will be fifth order. And the overall transfer function is just 1/2 times L3, so the overall transfer function will be fifth order. Okay, so this is, like I said, a pretty complicated system. It ends up being fifth order. But did you have any questions on the block diagram reduction that I exhibited here?
Yeah, I had a question. So in the sixth step, in the eliminating feedback loop, there's it says that there's like 1 minus GH and 1 minus, or 1 plus GH, right? Here we use 1 plus GH. I was wondering, like, when do we use 1 minus?
So if you look on the slide, there is a plus or a minus symbol in the diagram. And then that plus or minus symbol is inverted in the algebra.
Oh, gotcha.
Yeah, so if it's a negative feedback loop, you use the 1 plus form. And if it's a positive feedback loop, you use the 1 minus form.
Gotcha. Thank you.
Professor, would you ever see a reduction of poles as you condense the block diagram?
So what do you mean by reduction of poles?
Going from, say, a fourth order to a third order.
Yeah, so let's think about that. Could that ever happen? If I were to subtract like s to the 4 from s to the 4, then I would get something that's s to the 3. But we don't see a whole lot of subtraction in our block diagram reductions here. We're mostly just multiplying by stuff, yeah? So how could you reduce the number of poles if all you're allowed to do is multiply by fractions? Well, I think you've hit upon the concept of pole zero cancellation. So that's the idea, is that if you have a 0 in the numerator and a pole in the denominator in the exact same place, then they can annihilate each other. And that's funny you should ask, that's exactly what's going to happen here in this system. So let me pull up Matlab and show you how we can simplify this system using Matlab. Okay, so what I'd like to do is I'd like to run you through how to solve the previous problem using Matlab to help do your algebra reduction, basically. Remember we had something, the loop 1 was a transfer function that was a feedback path loop reduction. So the forward path transfer function in loop 1, I'm going to call G1. And there is a command in the control systems toolbox in Matlab called TF for transfer function. And the transfer function function takes two arguments, numerator polynomial and denominator polynomial. So just like in lab, where we defined our polynomials as arrays of coefficients, I'm going to do the same thing here. So the numerator in that path was 20, and the denominator was s squared plus s. Right, so that's 20 over s times s plus 1, but I distributed that s in, and I get 20 over s squared plus s. The feedback path there was, I think, 1 over s plus 2. No, s over s plus 2. So how would I write s over s plus 2? Well, that's 1s and 0s to the zeros divided by 1s and 2s to the zeros. And then loop 1 was the feedback connection of those two transfer functions. So feedback is another built-in Matlab function that, see if we can get the help file on it. There we go. So the syntax is system1, comma system2, where system1 is assumed to be in the forward path and system2 is assumed to be in the feedback path. I love the Matlab help files. They're filled with these little ASCII art diagrams, super old school. And then the assumption is negative feedback, which is exactly what we wanted in this case. Okay, so to remind you, Matlab tells us that the loop 1 transfer function is this, and I think if you were to reduce what I did on the whiteboard, you would get the same answer. Okay, so let's see. Loop 2, I think we can go ahead and just build loop 2 on our own. We don't have to use the feedback command here. So the numerator was s plus 1, so that's 1 comma 1. And the denominator was 4 times s plus 1 plus s plus 2. Okay, so I'm doing a little trick here. I'm using the fact that arrays act like matrices, and so I can add them like matrices, and I can multiply them by scalars. And so, oh, darn it. Sure. Yeah, that's what I meant. Huh, wonder why I couldn't add them like that. Anyway, this is actually what I wanted.
Missing a square bracket because you have a square bracket before the 4, and then I don't think you have a...
Thank you. Okay, so if I lose that bracket, okay, thank you, Shana. That's exactly what I wanted. All right, and then what do we got? We got loop 3 is the feedback connection of loop 1 times loop 2 in the forward path, and the transfer function 1 over s plus 1 in the feedback path. So sure enough, L3 is a 5th order transfer function. Now 5 poles and 3 zeros, right? This is a pretty complicated beast. The overall transfer function, don't forget that factor of 1/2 out in front of everything, is 1/2 times that. All right, so this is the final block that connects x to y in the example. Like I said, there's a lot of room for error here, which is why it's kind of helpful that we can use Matlab to do a lot of the menial algebra. So if you wanted to find out where the poles and zeros of this system were, there are a couple of ways to do that. So let's try and find the zeros first. Remember, the zeros are the s's that make the numerator 0. And another way to say that is they are the roots of the numerator polynomial. So I'm going to use the roots Matlab command. And roots takes an array as its input. And remember that array is the coefficients of the polynomial that you're trying to solve. And so to access the numerator array, I have to say t.num curly brace 1. So this tells me that there are zeros at -2 and 2 zeros at -1. So to find the poles, I'm going to do a similar expression, roots of the denominator of t and the first entry in that denominator array. All right, so Matlab tells me that there are 5 roots, 5th order polynomial, that's good. 2 of them are complex conjugates. 2 of them are repeated poles at -1. Oh, that's interesting. I had repeated zeros at -1 as well. And one of them is a real pole at negative 0.37. So I think this gets at what Connor was asking before. Is there a way to get rid of poles? And the answer is yes. You can cancel them with zeros. In fact, this 5th order transfer function on its face will have 5 poles. But once you cancel them with the zeros, which MATLAB doesn't do for us, interestingly, it actually will act like a 3rd order transfer function. So one way to visualize this is to have MATLAB plot the poles and zeros on the complex plane for us. So the command is pzmap, and this will probably pop into a different window. Yeah, there it is.
So even though it behaves as a 3rd order, we would still call it a 5th order?
So that's getting into the gray area. I would say I would call it 5th order, but I would qualify with saying that it will act like 3rd order. And let me show you why, like, saying that mouthful is important. If any of the parameters in the block diagram that we started this problem with were, I don't know, approximations. Like, so one of the blocks was s plus 2 over s plus 1. What if that was actually s plus 2.001 over s plus 1.000003? Right? Like, what if we'd rounded that? Well, then the poles and the zeros resulting from that wouldn't be exactly where we thought they were, and so they might not cancel exactly. So this is the nuance in this problem, is that, yeah, it was probably designed to act like a 3rd order system, but if you make some mistakes, or if there is rounding error or anything like that, you're going to have something that might look like a 5th order system.
Right. Thank you.
Yeah, you're welcome. Okay, so here is the full pole 0 map. We can see that the slow pole over here at 0.37 shows up, and the complex conjugate poles up here and down here show up. And then right here is actually where all the action is. There are 2 X's and 2 O's co-located right there. And then there is a 0 way over here at -2. All right, so like I said, if any of those parameters had been approximations, then if we zoom in here, we might get something like the X's and the O's don't exactly line up, and you would get something that behaves closer to 5th order. This is less of a concern because everything is in the left half plane. And I want to close the lecture with this warning, is that pole 0 cancellation is actually a fairly common technique. If you have a pole that gives you behavior that you don't want, provided that pole is in the left half plane, it is perfectly reasonable to try to place a 0 on top of that pole. And even if you miss, you'll get close and you will end up diminishing the effect of that pole. That's super common and actually a really good design idea. Everything I just said is wrong if the pole is in the right half plane. And I don't want to not say that. I want to really drill that home for you, because mathematically, there's no difference between a pole in the left half plane and the right half plane. It's just a sign change, right? Engineering-wise, they couldn't be more different. Okay, so this is the difference between taking a class from the engineering department or from the math department. The practical considerations of pole 0 cancellation in the right half plane are terrible. Because consider what would happen if you didn't have the pole exactly where you thought you did, or you didn't put the 0 exactly where you thought you did. Then instead of having a stable pole and a stable 0 kind of sort of canceling each other out, you'll have an unstable pole and an unstable zero not canceling each other out. But that, because it's unstable, the residue and the effect on the output will grow exponentially over time. Whereas in the left half plane, the residue will, or the contribution of that pole will diminish exponentially over time. So this is, I can't stress this enough. Pole zero cancellation is super good in the left half plane and super bad in the right half plane. Any questions on that?
So before starting a problem, is it a good idea to check if the poles are all in the left half plane before starting, just in case there's like a conceptual thing about asking if it could be an issue?
So that's a good question. And I want to say yes, like you should definitely know what you're starting with when you start a problem. But I also want to warn you that, like we saw at the beginning of the lecture, the poles of the subsystems are not necessarily the same as the poles of the closed loop system.
Okay.
Right. So we started this final example with none of the subsystems had complex conjugate poles. All of the poles were real, all of the zeros were real, and yet here we are at the end of the problem with two complex conjugate poles. So yes, you should analyze and figure out what you're starting with, but that's not the whole story. When you close these loops, the locations of the poles might migrate, actually will migrate.
So if we have poles and we realize that they're going to cancel, would it be a good idea to just leave it as like x plus 1 over x plus 1 and just have that in the problem but not cancel it until the very end just so you can know?
That's exactly what I would do, yeah.
Okay.
Oh, I had a question.
Go ahead.
We talk about the poles a lot, but do the zeros like not affect the system or what?
Well, the answer is no. They do affect the system. In fact, they can cancel the poles. So that's kind of what we were just talking about. But if you're talking about the characteristic modes of a system, those are entirely dictated by the poles. And remember, the modes are like the exponential functions where e to the pole times t. So that's what I'm talking about. Like some poles lead to bad behavior, some poles lead to good behavior, because the pole locations control the modes that are present in your output. Now, what do the zeros do? The zeros, if you think about back to your, what was it, Laplace partial fraction decomposition, if you change the zeros of the transfer function, they will change the residues of your terms in the output. So remember, the residues were the numerators of the partial fractions. So changing the zeros can change the residues. In fact, some of the times it can change the residue to 0, which is actually what we want in this pole zero cancellation example.
Thank you.
Yeah, you're welcome. This concludes Unit 1. Good luck, and I will see you in office hours.